In order to make the converter output to be stable and also controllable, we need to introduce a closed loop control and negative feedback. Then here's the questions. How can we quantify the stability evaluation of the system? How can we provide accurate guidance to the parameter design of the compensator? Both need us to derive the dynamic model of the converter. So this class we are going to introduce how to establish the AC equivalent circuit model of the DC-DC converter. So here, first let's talk about the background. So we know that in order to implement a controllable output, we need to introduce the closed loop control and also the negative feedback. In order to demonstrate those two concepts more vividly, so let me plot a block diagram for a typical power converter system. So we use a block to represent the power converter. We use rectangle here. So here is the power processor. And for the power processor, we have the, suppose the output signal is the output voltage. And there are three inputs. One is the input voltage, VGT, which is time varying. Second input is the load, which can be represented by the load current. So the load can be changing all the time. And the third one is the control input. For pulse width modulated converters, the control signal will be the duty cycle. So in order to establish a closed loop control, we need to introduce the feedback. So basically, we need to sense the output signal using a sensor module. So this could be an analog sensor or digital sensor, like analog to digital converter. Then we send this sensed signal to compare with our reference signal. So here is the reference signal. The reference signal means our desired level of the output. For a DC power converter, this could be a desired output voltage. Then we do the subtraction. We subtract reference voltage by the sensed output voltage. So the output will be the error signal. Then we need to have a compensator. Module to compensate the control loop to ensure a stable output. Then the output of the compensator is VC, is fed to the pulse width module. PWM module. The PWM module provides the pulse width signal, which is sent to control the power processor. So that is the entire closed loop block diagram of a power converter. So basically, for such a system, we need to properly design this compensator to ensure the system dynamic response is feasible. So in order to provide guidance to the design of the compensator, we need to model the system. So here's the motivation. So the control requires mathematical modeling of the dynamics. Only if we have the mathematical model, we can facilitate the design of the compensator parameters. So once we have the motivation, now let's try to think about how can we achieve this target. The basic idea is that so if we look at the spectrum of the output signal, we can plot the frequency spectrum of the output signal for the switched mode power converters. So here is the angular frequency omega. Here is the spectrum of output voltage. If we feed this output voltage to a frequency analyzer, we can decode the frequency components. Basically, there will be 3 parts. The first part will be the modulation frequency components. Suppose this is the omega m, the modulation frequency. Then we will have fundamental frequency component and higher harmonics. So this, we mark it as modulation frequency harmonics. Usually, this modulation frequency is pretty low. Could be hundreds of hertz or even lower. And to the right, we will have the switching frequency component. Usually, the switching frequency component will be omega s, will be much higher than the omega m. So in order to show the distance, we break the x-axis. This just means that they are farly aparted. So for the switching frequency component, we have we have such a omega s part, and also there are omega s plus omega m, omega s minus omega m. We call this as their sidebands. So basically, this is the switching frequency harmonics. And sidebands. And furthermore, to the higher frequency, we also have the switching frequency harmonics. So this is omega s. For example, we can have multiple times of omega s. We call this as the switching frequency harmonics. Okay, so we can see that although those two parts are both named as switching frequency harmonics, there are some essential difference. So this one is essentially the fundamental frequency. Fundamental parts. This is the higher frequency. Which means that this is the multiple times of omega s. So the basic idea to establish the AC model is that we can keep the modulation frequency parts while ignoring the switching frequency fundamental part and sidebands, and also ignoring its higher frequency components. So we can much simplify the circuit model. And also regarding the control system, you should know that the target is to realize a stable output, but there are disturbances. Usually the disturbance occurs in the input voltage or the load. For example, your input voltage could have the disturbances from the grid. And also the output voltage will be also varying continuously with the load demand. So both will incur disturbances. But we want to ensure that even if the disturbance occurs, the output voltage remain stable. So we need to properly design this compensator network and closed loop control to enable a stable system. Okay. Next, let's look at the mathematical basis for us to implement those modeling. So for a periodical signal, we know for power electronics, they have periodical feature. And the period equals to the switching period, Ts. So we can do the average operation. X. So xt is a periodical signal with switching period equals to Ts. This means that it's average over one switching period. So equals to 1 over period times the integral over one switching period at any time point, right? For example, at time point t, so with t in the center, we have one switching period from t minus to Ts over 2 to t plus Ts over 2. X tau d tau. There is a magic tool to analyze the periodical signal, which is Laplace transformation. Laplace transform. So the Laplace transform tells us in S domain, x, s. So S domain, this signal will be equals to a coefficient G average S times X S. And where GAV is the Laplace operator, right? So where G average S, for such a periodic signal, we have a formula to calculate. Basically, this is E to the STS over 2, which correspond to here, right? Minus E2 minus STS over 2 divided by STS. So that is the average operator coefficient in Laplace transform. Then we can replace S by J omega. So this become E2 J omega TS over 2 minus E2 minus J omega TS over 2 divided by J omega TS. We can use our mathematical tools to further simplify this. This can be converted to sinusoidal omega TS over 2 divided by omega TS over 2. So interestingly is that if we look at this item, this part is a real number. And it's frequency dependent. With the change of omega, the value of this quantity will also change. And actually, we know that for sinusoidal signal, if the sinusoidal part is very, very small, the sinusoidal of one small value will be roughly equal to this value, which means that at a low frequency, it could be roughly equals to unity, right? But that's only our intuitive judgment. We can use MATLAB to plot the profile of this signal in frequency domain. So in frequency domain, we can plot the magnitude of the average operator in decibel. Decibel means we do this calculation 10 times log. And the amplitude of GAV S. So this can be denoted in decibel, right? 10 log. So for the x-axis, actually we can use a normalized quantity as the ratio between the frequency and the switching frequency. So F over Fs. So then this will be 1, means the frequency equals to the switching frequency. And like here it's 2, 3, 4. And if we plot this in log domain, right? So here's like 0. Here is the minus 10 dB, minus 20 dB, minus 30 dB. Here is the minus 40 dB. Actually, here means a very, very small. That means the signal is much decayed. Then we plot the profile, we'll see that as we previously judged in low frequency, this will be equal very close to 1 because sine this value equals to this value. 1 in decibel means 0 dB. So we'll have this profile. And between 1 switching frequency to 2 switching frequency, we'll have such a profile. And same here. So the initial value is very flat, close to 1. So roughly here is 1/3 switching frequency. So if we look at this profile, we'll see that since this is a real number, means that there is no phase shift, right? Phase shift is 0. Furthermore, the amplitude at low frequency is almost a unity, means that this average will keep the lower frequency components. And if we look at the switching frequency part, 1, 2, 3, 4, we can see that those switching frequency parts are significantly decayed, right? So meaning that we can consider that this approximation will be accurate by doing the average over one switching period. We can keep the low frequency components and filtering out the high frequency, switching frequency, and the higher harmonics. So basically, this figure tells us that we can first preserve the magnitude and the phase of low frequency component. Especially the modulation frequency component. And secondly, we can remove the switching frequency and its harmonics. And thirdly, for frequency higher than switching frequency over 3, though the profile exhibits substantial attenuation. So that it provides us the fundamental of math knowledge. Okay. So in this section, we have introduced the AC equivalent circuit model for power converters. And we have learned that basically the AC equivalent model is an approximate model. It is achieved by first we do the average over one switching period. And secondly, we ignore the higher frequency harmonics, especially the switching frequency parts and its higher harmonics. So by doing this, we can achieve the linearization of the AC model.